Welcome 8th grade. How are you doing today? Building blocks of matter, which would be the structure of matter. We're going to talk about how all that works today. Now, matter. Anything that takes up space and has mass. So it's going to have volume and mass. We're going to give you examples of matter and then examples that are not matter. All right? Matter example, things like the air. Think about it. When it's trapped in a plastic bottle, you can't squeeze that plastic bottle all the way down. Air does take up space if it's trapped. Human. Desk. Gas like nitrogen and oxygen. All these things that you see in nature are likely matter. Things that you can touch, even like the air, some things you can't. All right? They take up space, they have mass, they're there. Things that are not matter. Heat. You can't touch heat. You can feel it, but you can't touch it, you can't trap it. All right? Light. There's no touching light. Ideas. Sound. Emotions. All these things not matter. Not tangible, not touchable. Now, Democritus came up with the idea for atoms. All right? He was a Greek philosopher. Atoms are small particles that make up most types of matter. He said this a long time ago. Okay? It was his idea. His first 4 types of atoms were earth, air, fire, and water atoms. All right? Now, what makes up matter? Hopefully we know this by now. If we don't, I've probably failed you. All right? Atoms, the small particles that make up most types of matter. Well, here's a picture of an atom, actually a model of an atom. All right, what are the parts? Number 1 here, we're pointing to this positive charge. That's a proton. And we need to know it has a positive charge. You don't? Well, I'm sorry, you get laughed at by your high school teachers. If you do, good job. All right, this one, outside the nucleus. This is the nucleus. Negative charge, it is an electron. And this one, inside the nucleus with no charge, it is a neutron or neutral. Okay, so protons, positive in nucleus. Neutrons, no charge in nucleus. Electrons, negative outside of nucleus. All right. Now, the law of conservation of mass is something that's important. The mass you end with is the mass you start with. We cannot create or destroy matter. It can't happen. That doesn't make sense. What about this? We have fire with all this wood, and then we have this. We have metal. When it rusts, we have that. How does that work? Well, Lavoisier weighed the wood and oxygen and fire, and then the ash and gas after the fire, and got the same weight. So, he had it in a small area. He was able to weigh the wood and all those things, and then the oxygen and the gases around it, they weighed a certain weight. When he got done, he weighed the ash and the gas and the wood that remained. He trapped all the gases that burned, and it weighed the same weight. He also did this with metal, oxygen, water, and the rust that results, and got the same weight for each. This was his proof of the law of conservation of mass. Mass cannot be created nor destroyed. It can change form, but can't be created or destroyed. Important. Models of atom, the evolution. So here's where we come up with the scientists and who discovered what and how it changed. Democritus came up with the idea of the atom. Well, then we had to figure out what does it look like. Dalton, matter made of only one type of atom. Oh, so he came up with the idea for the element. He called the atomic theory of matter. Okay, so his atomic theory of matter was created by Dalton. Dalton created the atomic theory of matter. Hint, hint. All right. Then there was this gentleman who discovered electrons with cathode rays, and we'll show you how he did that. J.J. Thomson discovered the electrons with cathode rays, and we'll show you what they did. Rutherford, he said atoms are made of mostly empty space. This is where you get the guy that compared, if you had that whole football arena, and you put like a quarter or a dime on the 50-yard line, that quarter or a dime would be the nucleus. Or maybe if you want to think of a bouncy ball for 3D, the rest of the stadium would be the electron cloud where the empty space is. Yet, when we touch stuff, it's solid. He came up with that atoms are made of mostly empty space. Rutherford did that. Want to know the scientist? Named the nucleus. Okay. He discovered protons and said they are in the nucleus. And electrons are outside the nucleus in mostly empty space. Thomson discovered the electrons. Rutherford said where they're at. Rutherford did quite a bit, but he couldn't figure out this weight disparity. So there was a guy that discovered neutrons with cathode rays, and that was Chadwick. Chadwick and Thomson used the same kind of experiment. Chadwick realized, oh, these neutrons, these have to be something different because of the way it's acting. This page, take time, screenshot it, boom, you get all the information on all the scientists you need. All right, pause it, screenshot it, got all the scientists you need. We go on. Dalton. Matter is made up of only one type of atom. It's called the atomic theory. I'm talking about this scientist a second time. And you can see a little bit more about Dalton as you read there. Now, J.J. Thomson, he discovered electrons with cathode rays. So, he made these cathode rays. He put a positive up here and negative up here. Now, we know he shot these particles through. These particles started to repel the positive. Well, if we think like charges repel, like with magnets, remember how you try to push the magnets together and boom, they push apart? Same thing happens. So if this particle is going away from the positive, we know it is probably a proton, because protons are positive, positive charge, it goes away from the protons. Oh. Other particles were shot through, they went straight. Nothing happened. They didn't repel the positive, they didn't repel the negative, just straight through. They be the neutrons. Then they shot other stuff through. The negative charge up here, the positive charge, went through, started to go away from the negative, repelled the negative. That be the electrons. Okay. That's the experiment that they used to discover this. Remember, Chadwick discovered the neutrons, Thomson discovered the electrons, but they used this similar experiment to figure out which were which. Then, Thomson's model looked like this. Kind of looks like a chocolate chip cookie. All right? He said this is the atom. The electrons are just negative spots stuck into it like chips in a chocolate chip cookie. Not the best model, but it was very good for that time. All right? Then, Rutherford. Atoms made of mostly empty space. They discovered protons and said they are in the nucleus. Electrons are outside the nucleus. Well, how did he do this? He used, and please bear with me. Yep. He used the gold foil experiment. So like you have aluminum foil, he rolled gold into the thinnest possible foil that he could. Then he took lasers and emitted high energy particles. Well, he found out some of the particles went right through. Most of them actually did. Do you see how the stream continues right here? Most of those particles go right through the foil, no problem. That got him thinking. If most go right through untouched, atoms must mostly be empty space. If most of the particles can go right through things. Okay. Some of the particles, though, ricocheted off and changed direction. You can see all these little arrows coming out. Others of them stayed the same direction, or came even back. All right? So, his gold foil experiment allowed him to do that. You may want to put that the gold foil experiment was with Rutherford. All right? Then, Chadwick discovered neutrons when the streams of particles were unaffected by electronic fields. That positive and negative charge, they went right through. Oh, must be neutrons. All right, no charge. Now, improving the atomic model. Another scientist just comes up. We have Niels Bohr. Right? He discovered energy levels with orbits. Continued research showed no orbits, not obits, orbits, but electron cloud. So he's thinking, oh, there's an orbit they go around, kind of like the planets. And then another orbit, and another orbit, and another orbit. All right? So once they fill the first energy level with 2, then they go to 8 for the second one. Once that 8 is filled, they go to 8 for the next one. Then they go out to the next one, and there's 18 there. That actually wasn't the case. But if you'll see, there's darker areas here. There's a cloud that is so wide, and it covers it, kind of thinking like a ball inside of a ball. All right? That's a darker area where they're likely to be. And then you can see there's another darker area out here. That's the second level. That's where those 8 are likely to be. So it's not really an orbit, but it's a cloud where they're likely to be. Kind of think of fog. Fog, when you see it off in the distance, it looks very solid. The particles are there. When you get closer, you can't see them. That's kind of what they imagine this to be. They're moving so fast that you see that blur that they cause, but we don't know where in that space they are. All right? Then the smallest known particles, that's changed. All right, 370 BC, atoms. 1930, protons, neutrons, and electrons. Recently, and when I say recently, probably the last 10 years, 15 years, all right, we have quarks. Quarks are the things that make up protons, neutrons, and electrons. One has an up spin, a down spin, a strange spin, a bottom spin, top spin, and a charm spin. All right. We don't know exactly how these work, but physicists are at this time period looking and making sure they can try to figure out how these survive. All right, guys, there's everything you need to know. Have a good one.